Welcome back. Today we're going to talk about the second half of 6.1. So we've been talking about vectors and what it means to add vectors and kind of have that magnitude. So to go magnitude in a given direction, to have the components and to put two vectors together. So let's talk about a couple of different nuances that go with this. Unit vectors. A unit vector is a vector of magnitude, so of length 1. So this is the length of the vector is equal to 1. And so these unit vectors have a length of 1, and so that's, you do the Pythagorean theorem on them to determine the magnitude, and it's going to be 1. So directional vectors, so these two parts kind of go together, so I'm going to have some explanations, and I need to step over here, and I'm going to give you some more of the piece of the information. Direction vectors provide a direction for unit vectors. Okay, so you'll have a unit vector in the direction of, say, 3, 2, something like that. And so what we've got over here is u is equal to v over the magnitude of v, which is 1 over v times v, where v is a non-zero vector. Okay, so this is like, we've got a vector v. This is our directional vector here, right? So v is going to be our directional vector. So you're probably like sort of lost right now. Let's look at an example and you'll kind of see how this works. So find a unit vector in the direction of v equals -3, 2 and verify that it has length 1. And so what you're imagining is you've got a vector in the direction of 3, 2 that's only 1 unit long. And so what we're going to do is, so v equals 3, 2, -3, 2. And so if I want to find the magnitude of v, it's going to be equal to -3 squared plus 2 squared, and the square root of that, which is equal to 9 plus 4, so the square root of 13. And so if I've got a unit vector like this, v over the magnitude of v is equal to -3 over root 13, comma 2 over root 13. Okay, so that is a unit vector in the direction of v equals -3 comma 2 and verify that it has length 1. So what does that mean? So what I'm saying is, okay, it's in the direction of 3, 2. Let's just say -3, 2 is this way. It's not, but let's say it is. Okay, it's in the direction of -3, 2, and it has a length of 1. So the length of my arm would be 1. Okay, so what would be the components here that would make it so that this is length 1, right? But the components are, they can't be 3 and 2 because then this will be root 13. Does that make sense? So you take each of the components and you divide by root 13. And so to verify that, you'd say verify, okay? That would be -3 over root 13 squared plus 2 over root 13 squared, and you take the square root of that. So what we're saying is, hey, you've got this vector of length 1. It's the length of this pen. This is 1. What are the components that have to go into it? So you take the components and you divide by the total length, because when you square them, watch what happens. This becomes 9 over 13 plus, because it's -3 squared, which is 9 over 13, root 13 squared, plus 4 over 13 is equal to 13 over 13, and this is what we're taking the square root of this, right? And that's the square root of 1, which is equal to 1. Okay, so that's us verifying that it has a length of 1. Okay, and you do the same thing in this example here to find that. Standard unit vectors. Standard unit vectors, this is an alternate notation. And the standard unit vectors look like this. I is 1 comma 0, and j is 0 comma 1. Well, what does that do for us? So if I've got a vector equal to AB, right, it's going to be equal to A comma 0 plus 0 comma B, right? So those two components together, I could add them. So this would be equal to A times 1 comma 0 plus B times 0 comma 1. And I'm seeing, so this is I, so 1 comma 0 is I, so this is AI plus B times J, right? So that's an alternate notation. So A and B are the horizontal and vertical components, and so that's going to be another way to write this. So how do we do this? Another alternate notation would be this. If we have any given vector, okay, let's say it's, vector v shooting out this way. Its horizontal components and its vertical components are going to look like this. If v was equal to 1, it would be like the unit circle, right? So it would be cosine and sine. And so if I have v is 2, or v is 5, or root 16, or 2.8, whatever it happens to be, the components are going to look like this. Okay, and so the components are going to be the magnitude of v times the cosine of v. So v is equal to v cosine theta, magnitude of v sine theta. Okay, why is this? Well, we remember that if v is a unit vector, it's equal to what we talked about up here. I'd find the magnitude, right, and I would divide v by the magnitude. And so if this is v over the magnitude of v, and these are going to be v magnitude of v cosine theta, magnitude of v sine theta. Those components match up with the unit circle. So we're thinking, so these things are now tying together, right? So if in the unit circle v is equal to 1, so cosine theta sine theta makes sense. If it's not 1, then it's going to be v cosine theta, magnitude v sine theta. Okay, so that's what this means. This all goes with direction angles, because our vectors this way have a component of v sine theta and magnitude v cosine theta, right? And so what do we do with this? So it says find the components of the vector v with direction angle 115 and a magnitude 6 using no technology except to approximate the exact trigonometric solution. So let's just look here for a second. If I've got a coordinate plane here, and this is 115 degrees, okay? Let's say that's 115. What happens is I have a couple of components here. They're gonna make up this. So v is equal to AB, right? So my vector has two components, and so that would be the magnitude of v cosine theta and the magnitude of v sine theta. Well, what does that mean? Well, if I have a magnitude of 6, that's going to be 6 cosine 115 comma 6 degrees is important here, times the sine of 115 degrees. And that's it, folks. That's it. So it's going to be equal to approximately, and I'm going to write squigglies here, approximately negative 2.54 and 5.44. Okay, so once we know the magnitude and the angle, we can resolve the vector. Same thing down here. This is another example. You can go ahead and do that one, but you're going to end up with a pretty straightforward answer just like we did up here. Find the magnitude and direction of direction angle of each vector. Okay, so magnitude we know how to do. So magnitude here is this is the square root of 3 squared plus 2 squared is equal to the square root of 13. Okay, So that's the square root, so square root of 13. So the direction, I'm going to need to draw a picture. So let me draw you a little picture here. Got my coordinate plane here. 3, 2 would be up this way. So I've got 3 and 2. And this is my direction angle here. So how do we find that? Well, my direction is the magnitude of v times the cosine of theta, comma, the magnitude of v times the sine of theta. All right, so I know that this is root 13 cosine theta, comma, root 13 sine theta. But what's my theta? In order to find my theta, I've got to figure out this angle here. We'll check it out. So if this is 3 and this is 2, this is root 13. That's magnitude. All these things are tied together, yeah? And so my angle, so theta is equal to, how do we find an angle given sides? Well, we would do the inverse cosine or the inverse sine of adjacent over hypotenuse, okay? Which would give me an angle approximately equal to 33.69 degrees, making sure our calculator's in degree mode. And so that would mean that it's root 13 times the cosine of 33.69, comma, root 13 times the sine of 33.69. Okay, so you kind of see we are going back to all of the things we talked about in chapter 5, and we're working on making them like putting them all together, right? And so the direction angle is 33.69. And my magnitude is 13, okay? That's all there is to it, fellas and ladies. That's it. That's all there is to it. We've got a couple of examples here. A DC-10 jet aircraft is flying on a bearing of 65 degrees at 500 miles per hour. Find the component form of the velocity of the airplane. Recall that bearing is the angle that the line of travel makes with due north measured clockwise. Whew. Okay, what does that mean? Let's draw a picture. I've got an airplane flying at a bearing of 65 degrees, makes with due north, right? So if this is north, then that means that this measured clockwise is 65 degrees, right? And so it's traveling at 500 miles per hour. This is the magnitude of the vector. Okay, so this is 500 miles per hour, which means that this down here is my theta, right? Because really I'm measuring this right here. I've always got to measure it with that x-axis, right? Those reference triangles that we've been talking about so much. And so if I'm trying to find the component form, I want something that looks like this. Magnitude of v, cosine of theta, magnitude of v, sine of theta. Well, the magnitude is the speed, so this is 500, and I determined that my velocity was my speed here is my magnitude. My theta is based on that reference angle right here, okay, with the x-axis. So they give me 65, but I deduce 25, so this is cosine of 25, and then this would be 500 sine 25, right there. Okay, so roughly we're talking this, 453.15, comma, 211.31 on my components there. Okay, so what's tricky about that? Knowing that speed is dealing with my magnitude, and also knowing that my angle has to do with not just what they give me, but deducing that it has to be with that positive x-axis. All right, pilot Megan McCarthy's flight plan has her leaving San Francisco International Airport, flying a Boeing 727 due east. Okay? There's a 65 mile per hour wind with a bearing of 60 degrees. Find the compass heading McCarthy should follow and determine what the airplane's ground speed will be, assuming that the speed with no wind is 450 miles an hour. Okay, there's a lot here. Let's look. I'm going to draw a picture first. So if she's going due east, this is our direction here. And the wind, a 65 mile an hour wind, so that's this. bearing of 60 degrees. So this is 60 degrees here, and this is 65 miles per hour. And so my plane is going to be, you know, somewhere in here, right? Because if my direction is this way and the wind is blowing me, yes, so we've got to add. The wind vector plus the plane vector is equal to my actual, right? I'm looking for where I actually have to go because I want to go east, but my wind is, so if I'm going east and the wind is blowing me, right, in a plane, so I've got to travel, you know, slightly this way in order for the wind to blow me back. And so what I need to do is I need to add the wind plus the plane. So let's think about, we have the wind here, right? We've got the 65 miles per hour, which is the magnitude. We have the bearing of 60 degrees. And so we're going to need to take into consideration this angle here, right? Because that's our due east. With my plane, I'm going to need to consider this angle here, which I don't know. But I do know that the airplane's speed, so I know that this is 450, right? So 450. And so let's take a look here for a second. My wind vector looks like this. This is 30 degrees down here. And so my wind vector is 30 degrees, no, sorry, 65, because it's 65 mile an hour wind. It's going to be 65, and that's times the cosine of 30, comma 65 sine of 30. Okay, and I can kind of in the back of my mind see that I'm going to know these from a unit circle, right? My plane, for whatever else, I don't know my theta, but I do know that it's going to be 450 cosine theta. I don't know what it is. This is theta here. And then my y component is going to be 450 sine 30. 450 sine theta. Okay. When I add these together, let's look at exactly what I've got here. Okay. I have 65 cosine 30 plus 450 cosine theta, comma, 65 sine 30 plus 450 sine theta. Well, what have I just done there? Right now, I've just figured out what the actual is going to be. So factoring in the wind and the direction that the plane is going, I figured out where I'm actually going to go. Well, here's the thing. I actually want it to equal due east. I want this component vector to equal due east. And so what does that mean? Well, it means that my vertical component, so if I'm going due east, think about it like this. I want my vertical component to equal what? Well, if I've got vertical component here, it would be this, right? So if it's due east, think about it for a second. That would mean that's the sine theta. Well, what's the sine of theta over here? Due east is equal to a vertical component equal to 0. Okay, so I need to set my vertical component equal to 0. So that means that I have 65 sine of 30 plus 450 sine of theta equal to 0. Okay, and so if I solve this, I'm going to do minus 65 sine 30 minus 65 sine 30. So this goes away. So I have 450 sine theta equals minus 65 sine 30. Because I need to find the angle, right? I need to find what this angle here is equal to. That's what I'm solving for. That's the direction I need to go. Divide by 450. Divide by 450. So the sine of theta is equal to negative 65 sine theta, sorry, sine 30. Sine 30 over 450. So to find an angle, knowing a big long decimal, I'm going to do inverse sine. So theta is equal to the inverse sine of negative 65 sine 30 over 450, which is equal to negative 4.14 degrees. Okay, so that means that my angle is negative 4.14 degrees. Why? So what do we just do? Okay, wind is blowing this way. I want to go this way. I want to go this way, straight east, right? Well, if the wind is going to, so I travel straight east, it's going to blow me off course. Well, how much? This is course correction, right? So I just figured out that my component vector, my component form of my vector of my wind, right here, right, is this. The component form of my plane is here. I know how fast I'm going, but I don't know what direction I'm going. That's this. And when I add those two things together, I want to get due east. Okay, I don't have enough hands, but I want to do this. So my hand is the wind. This black one is the plane, and I want to end up due east. So I said, what I know plus what I don't know is equal to this. So I did exactly what I know. I know that this equation right here gives me the component form. Wind plus plane, the components. And I want my vertical component to equal 0, right? It's due east. And so what I said was I'm just going to take one because theta has to be the same in both. So I took my vertical component here and set it equal to 0 because there's no vertical component of my due east vector. And I solved for sine to find that my angle was negative 4.14 degrees. So that plane has to set off at negative 4.14 degrees to get there. Well, what does that mean? So what I need to find is the ground speed. When I get in the direction vector. This one here, right? And so what does that mean? That's going to mean the ground speed of the direction vector is the square root of, now think about this for a second. What's my vector? My vector is the sum of these two vectors, right? So the sum of these two vectors is 65 cosine 30 plus 450 sine negative 4.14, right? Squared plus 0 squared. Why 0 squared? Because it's due east, right? So it's due east, so that's 0 squared. So when I do the square root of that, and I put all that into my calculator, I get that my ground speed is equal to 505.12 miles per hour. Okay, that's how we figured that out. So they wanted us to know, well, how fast is it going? Because I know the direction. How fast is it going? And I needed that angle to be able to help me find that ground speed. Okay, guys, if you have questions, please reach out to me. But thanks for watching, and we'll see you next time.